what I recommended is, let's say, let y be sine inverse of 2x. Now, what I wrote in solutions is, first of all, I said, okay, so let's call z 2x. dz equals 2 dx. So first I changed the inside, denoting it by whatever letter you want. Z equals 2x, dz equals 2 dx. So I made the adjustment for 2 and 1/2. So forget about this for a moment, for y. So this is 1/2 the integral. Do not copy the limits of integration yet. So 2 and dx, you see it here. 2 and dx will be dz. This piece is sine inverse z, and the denominator is the square root of 1 minus z squared. Do you agree with this?
Yeah.
Now I will use y as being sine inverse z. So when I differentiate both sides, I get that dy equals 1 over the square root of 1 minus z squared dz. Right? So when I differentiate sine inverse, I get of z. I get 1 over the square of 1 minus z squared. Agree? Times dz. And look what I have. This is y. This is dy. So I have 1/2. Not so fast. I have to change the limits of integration first of all. So when x is 0, z is 0. When x is 1/4, z is 1/2. And now I move to 1/2 the integral from y dy. And I have to change the limits of integration again. So one more time. This is y, and this is dy. So now, when z is 0, sine of which angle is 0? Good. That's okay. And now, when you're way ahead of me, like always. So now when z is 1/2, what angle has sine 1/2? He already told us, Noah.
But one would use the other one too.
What do you mean?
Since wouldn't every 2 times that sines and negatives 1 would be 1/2? Or
So z is here.
Mhm.
Z goes from 0 to 1/2.
Oh, it's not in balance. Okay.
Right.
Gotcha.
So when z is 0,
Mhm.
sine inverse of 0 is 0 radians.
Mhm.
When z is 1/2, sine inverse of 1/2 is pi over 6. Pi over 6, 30 degrees. But I have to use pi over 6. So finally I have 1/2 y squared over 2 from 0 to pi over 6. Of course, leave the constant outside. That's the best thing to do. And you just plug in pi over 6 and you square that. And when you plug in 0, you get 0. So the answer is pi squared over 36 times 4. How much is 36 times 4? 144. Is this clear?
How do you,
Yes?
like, what do you see when you first look at a problem? Like, how do you know you?
Right. Excellent. So I copy everything from your book. So this problem is in your book. But regardless, when I look at the original problem, and that's a perfect question, I see sine inverse. When I see sine inverse, I say, okay, sine inverse is okay, but sine inverse of 2x is not okay. Because it's a function inside sine inverse. If I only have sine inverse x, I'll say, well, plain sine inverse, but this is not the case. Secondly, I know that sine inverse prime is 1 over the square root of 1 minus something squared, right? So when I see that here, I see the square root. I see that function prime here. in the denominator, which is 1 over, right? So there must be a combo. I have to get rid of sine inverse. I have to get rid of 2x, because it bothers me inside of a function. And then I have to think in terms of denoting sine inverse by whatever, because the derivative of sine inverse is already in the problem. It's a very good question. So when I differentiate sine inverse, I know I get 1 over. Sine inverse z is 1 over the square root of 1 minus z squared, and that is in the problem. So remember the substitution. Whatever you choose, the derivative of that, basically the differential of that, should be in the problem. If 1/2 is not in the problem, I can make it. But if x cubed is not in the problem, I may not be able to make it. But it is, the differential of sine is in the problem. Better? Okay. Yes, Betty?
Is there a way to be able to, like, a problem like that, be able to split that up and do the integrals of both of them?
No, because this is not a sum or difference.
Okay.
Very good question. So, remember we said when I take the square root from 2 and 3, you can say the square root of 2 times the square root of 3, right? But here I have a function, and I cannot separate them, the two pieces. So if it were a sum, yes, I could have. Very good question. So if I have something like this, the integral from 2x plus x squared dx, yeah, of course. But if I have the integral from secant squared x times tangent x d theta, I cannot write the integral from secant squared d theta times the integral from tangent theta d theta, because it's a product. So if it's a product or a ratio, I can't. But if it's a sum, yes, of course. Good. Next problem, next question.
Can we do 11C?
Yes. What does it say? 11C. Yes. You tortured me with that one.
I couldn't figure it out.
Good. So the first part is clear. It's x to the 10th over 10 plus, right? 9 to the x over natural log 9 from 0 to 1. Let's take a moment and differentiate. When I differentiate, this is a constant, right? When I differentiate a to x, I get a to x times natural log 9, which will go away with that, and I get back that. Is that okay?
Yeah.
So you can still verify this before you plug in the numbers. After you plug in the numbers, it's gone. It's done. You can't do anything about it. So now we have to plug in the numbers, and we plug in 1. And we get 1/10 plus 9 over natural log 9. But careful now. You must plug in 0. Here's why. Here, this will be gone. But here, when you plug in 0, not here, this is natural log 9, it's just a number. When you plug in 0 here, you get 1. So it's minus 1 over natural log 9. And this problem was done in class. You just want to torture me. That's it. I know now.
I was throwing like absolute values and crap into there to figure out how it cancels out.
Because you understand that this is not the integral of 1 over x. The integral of 1 over x, yes, it will end up in natural log of the absolute value. So we are here integrating a constant raised to a number. Always refer back to e to the x. If you keep that in mind, you will never make a mistake. So let's go back for a second. So if I integrate e to dx dx, I know the answer, right? It should be multiplied by natural log e, but it's 1. So if I integrate a to x dx, it should be divided by, natural log e. e to the x divided by natural log e. Here I have a to x divided by natural log a plus a constant c. Because when I differentiate this, I get a to the x times natural log a over natural log a, which is a constant. I don't differentiate the denominator. I differentiate the constant is 0, and then these two go away, and I get back a to the x. So this would have been natural log e to the x over natural log e. But there is no need because natural log e is 1.
Can you do,
Yes?
11F?
11f. Yes. So in 11f, we have the integral from e to the x dx over the square root of 43 plus e to the x. So yes, of course, what bothers me here is that 43 plus e to the x. So I'm going to say this is y. As long as dy, which is e to the x dx, is in the problem. Yes, it is. So I don't have to do anything. Yes, some of these integrals really look fantastic, but they're really nothing. There's nothing there.
Yeah.
Right?
Yeah.
It just looks so, it pokes you in the eye with e to the x and the square root and everything, but it's really nothing. So then I have y to 1/2 plus 1 over 1/2 plus 1 plus a constant c, and this is 2 divided by 3. And you can write it as 43 plus e to the x raised to 3/2 plus a constant c. Some of you put the square root, that's fine too, whatever. Yes, ready?
Can you fully explain this is kind of dumb? The whole going back and forth from different square roots to
Say it again? You mean this part?
No, I've always had trouble with square roots and going back and forth from a fraction to a square root.
Oh, yeah. So every time we see a fractional exponent, so if I have the square root of 2, this is 2 to 1/2. 1 being the power, and the denominator of the fraction being the index. So if I have the cube root of 2 squared, this is 2 raised to 2 over 3. The denominator is always the index. So now if I have, let's say, 43 plus e to the x raised to 3/2, this will be the square root. This is the index. The denominator is the index. 43 plus e to the x to the 3rd power. You can continue to simplify this because 3 divided by 2 is more than 1. I can take the integers out. So I can write it as 43 plus e to the x squared multiplied by 43 plus e to the x. Because 43 plus e to the x to the 2nd power times 43 plus e to the x to the 1st power will give us the 3. Copy the base, add the exponents. But this I can take out of the radical now if I want to. So fractional exponents, the denominator is always the index, the power is the power of the base. Is that kind of what you wanted?
Yeah, that's exactly.
Okay. Good. Next question. All I wanted here is for you to write the total distance with the absolute value. That is the key. If there is no absolute value here, then you will not get the total distance. So please remember that. Anything else?
question, right?
Yes,
After you substitute in for I, it's gonna have you
yes,
the simplification, I guess that's.
yes. So after we substitute for, you mean for xi, right?
Yes.
Yes. So the function becomes so I took out 2 over n. So did you get 8i squared over n squared n plus 2i over n plus 3?
Yeah, so I got it all the way down to the 3 different sigmas,
Yes.
and then how to,
So
And then I
2 over
converted
n
it
is
to-
in front.
yes.
Then we have 8 over n squared
Mhm.
times n plus 1 to n plus 1 over 6. Some of you wrote 2 in the denominator. Some of you wrote 3 in the denominator, but it's 6. We have no choice. And then 2 over n, and then n plus 1 over 2, and then 3n. Did you get this?
Yes.
Okay, so here what I recommend is keep 6n as the least common denominator. Do not simplify anything else but just the n, 1n. And then the numerator of the first fraction becomes 16n squared plus 24n plus 8.
Mhm.
And then plus, the second one has to be multiplied by 3 at the top. So you have to have 6n squared plus 6n. And then the last one gets a 6n, which makes it 18n squared. So then when you combine like terms, you end up with 40n squared plus 30n plus 8, and I simplified it 2, so the denominator now is 3n squared. Is that better?
Yes, thank you.
Thank you. Yes. Next question. Number?
8.
Number 8. Where is number 8? Yes. Okay, so for number 8, the integral from 0 to 4 is this area. So this area can be determined in several ways. One way will be to say this, which is 4 times 2, plus height, base times height divided by 2, 2 times 2 divided by 2. Hold on. Let me see what I did. I calculated differently here, so times 4 here, yeah. Yes. Right, so hold on. So I have 4 times 2 plus 4 times 4 divided by 2. Got it. So this is 8 plus 8, which is 16. That's how I got the 16.
I didn't count it as 2, I counted it as 1.
Oh,
Same. I caught that like halfway through. Had to go back.
so then the integral from 0 to 12 is everything till here. So everything, including this, but this piece is identical with this piece, and they're opposites, and I will not even calculate them. I will add to this piece, which is already 16, I will add this piece, or this, and then this. So this height is 2 times 6, which is 12, or 3 times 4. And now let's see here. This is a trapezoid. The height has to be estimated. Not the small base is 5. 5 plus 6. So 5 plus 6 and multiplied by the height, which is 2, divided by 2. So it's plus 11. So I calculated differently here. So I consider these two identical because they seem like it. So I have to add to 16 one more time. I'm adding 2 times 6, which is 12. So 16 plus 12. And then one more time I got here, for this I got 11. So did you get 16 plus 12, 28, did you get 37? Yes? Okay.
You're supposed to estimate like to whole numbers.
Say it again.
You're supposed to estimate to like whole numbers.
Oh, it is a whole number, 37.
I mean, for like looking at each cube.
No, it depends. So this is between 2 and 4. Oh, did I say something else? So it's 3? Oh, yeah.
No, it's just like all your estimates are in whole numbers. I was just wondering where you're supposed to estimate it with whole numbers.
It depends on where it is.
Okay.
So you're just going to come up with your best estimate. But I think I multiplied, so let me see, 3, 3. So base, okay, this is 3. This is 6. That's 9. And this is 2 over 2. Okay, so sorry, hold on. So 16 plus 12, that's 20, yeah, 37. Okay, number 3, or part C. For part C, we go to from 10 to 14. So for part C, they only want this, from 12 to 14. So this is 3. This is 6. And this is 2 over 2. So it's it is 2, 4, 6. 2, 4, 6. Right? And this is 3. Okay, so it's the same with this, and I wrote -9. So 4 times 6, how did I get 4 times 6? Oh, yeah, it's from 10. Sorry, it's from 10. Okay, so this piece is correct. It is -9. That's correct. And I have to add this piece, yes. So I use the triangle, yeah. So the triangle is base times height divided by 2. So this is 4 indeed, and this is 6 indeed, divided by 2. Yes, that's how I got -12.
Is the 2 in the numerator for the area of the trapezoid, is that constant or is that dependent on
You mean this one?
the one on top? The 3 plus 6
Yes,
times 2.
so it's just this piece. So yes, this is always the formula.
Okay.
Small base plus big base, 3 plus 9 plus 6, multiplied by the height, 2, divided by 2.
Divided by 2.
Yes,
Constant.
always. It is like the triangle,
Gotcha.
base times height divided by 2.
Okay.
So for the trapezoid, is small base plus big base times the height divided by 2.
Gotcha. All right.
Okay, and now the last one, 0 to 18. So it's the whole thing. So the whole thing from 0 to 12. From 0 to 12, I already have the number 37. And then I have to subtract this area. But I already know that this is -9. And I have to determine this area, which is 6 plus 4, which is 10 times 4, right? 10 times 4 divided by 2. So this is 20. So that's exactly what I got. 37 minus 20, which is this one, minus 9, which is 8.
That's not a bad problem, actually.
No.
I think if I knew, like, if it was embedded of how to see the big base and the low base, because I knew the formula, but I guess I
Okay.
didn't see the bases. But now I understand that. Okay.
Good. Other questions from this? Yes, Betty?
So what's the, Because under one of the graphs, we constantly go up, isn't that? Fine, where the area will always have, it wasn't on here, I understand how this graph works. Okay, cool.
Yes.
When we were looking at the other graphs, they constantly went up. They never,
Do you remember which problem that was? Yeah, please do. Okay, I want you to talk about this for a moment. Please remember you have to multiply by the inner function prime. So you cannot just simply replace u by 1 minus 3x. You also have to multiply by the inner function prime. The same thing here. You have to multiply by the inner function prime. If it's x, then you don't have to because x prime is 1. But if it's anything other than x, you have to multiply by the inner function prime. Anything else from this test? Okay, so let's go back to other tests or other problems that you would like to see. Anything else? Yes?
For test 2, chapter 3,
Yes?
I was wondering if we could do 1B.
Can I copy it?
Yeah, of course.
Thank you.
That,
Which one?
this one,
Yes.
and also G.
Yes. Yes, so let's start with G because it's much shorter. So G, y equals 9x e to negative kx. And I'm going to copy y, which is 3x squared minus 1 to the third, divided by x squared plus 3 to the fourth. Yes, no idea. What did you have in mind?
I just had a random web design question.
Yes, and then we'll do that. Is that okay?
Yeah.
Okay, so here we want to differentiate. Leave the 9 outside because it's a product. So differentiate the product. So from here I have y prime equals 9. Every time I differentiate a product, I have to get a sum of 2 terms. So when I differentiate x, I get 1. So then I have to keep e to negative kx. Then I keep x. I multiply by e to negative kx, but I have to multiply by the inner function prime, which is negative k. Is this okay?
Right, because K was the constant, right?
Yeah, because when I differentiate negative kx, I get the constant negative k. I will factor out e to negative kx because I can. And I have in parentheses 1 minus kx. The reason why we normally try to factor, right, because now you know we do a lot of work with derivatives. We set them equal to 0 and we find this and that, critical numbers, etc. So we really want to keep it in a factored form. And it also looks much nicer. You can also present it if you like. There is no need, really. 1 minus kx divided by e to kx. Why do I, not just me, in general, we insist no negative exponents in the final answer? That is a better, because when I set that equal to 0, you will never attempt to say, oh, e to negative kx could be 0, because you can't. So once you bring it to the denominator, you'll never say e to kx must be 0, because you can't, first of all, and you shouldn't, because it's in the denominator, but e to kx will never be 0. So when you set that equal to 0, you will say, oh, x is 1 over k. Okay, so now the other one. We have y equals 3x squared minus 1 to the third over x squared plus 3 to the fourth power. This is not a friendly problem for many reasons, right? Because differentiating it is not a big deal, but then I have to factor and fully simplify it. And that is not easy. So let's do that. We must use the quotient rule. When I differentiate the top, I get 3x squared minus 1 squared times 6x. If I miss the 6x, the whole thing collapses. I won't be able to get the answer. So I differentiate the function to the third power. I bring 3 down, I subtract 1 from the power, and I differentiate the inner function. Now I have to multiply by the denominator, and then minus. I copy the numerator, but now I differentiate the denominator. And don't forget, the denominator gets squared. So 4 x squared plus 3 to the third power, and you're not surprised, times 2x. I don't have room. Okay. Now, at this point, I have to look for factors, as many as possible to pull out from the numerator. So, of course, a 3x squared minus 1 to the second power will come out. Of course, an x squared plus 3 to the third power will come out. And now let's see what I have here. I have an 18x, and I have an 8x. So a 2x as well. Out, out, out. So 2x, 3x squared minus 1 squared, x squared plus 3 to the third, out, out, out. Okay, let's take it easy and see what is left in brackets. So from 18x, I took out 2x. So I still have a 9 in there. This is out. From these 4, I removed 3. So I still have an x squared plus 3 minus. Now 4 times 2x is 8x. I took a 2x outside, so I have a minus 4. And now this is completely out, but from this one, from 3, I removed 2, so I still have a 3x squared minus 1. Only now I can do this. Only one that is completely out, a factor, only now I can simplify. So now the numerator is 2x, 3x squared minus 1 squared, 9x squared plus 27 minus 12x squared plus 4 over x squared plus 3 to the 5th power. There's nothing else I can do except combine these and potentially pull out the negative sign. Okay, so 2x, 3x squared minus 1 squared, and this is negative 3x squared and plus 31 over x squared plus 3 to the 5th power, and yes, I will pull out negative in front. And now you know why, because we work with these derivatives a lot. And we either want to set them equal to 0 or study their sign, blah, 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 right? So we want that to be as simplified as possible. Is this better?
Yeah.
Okay. No one next question? Hold on, he was next, and then you're next, Eddie. Did you find the one that you were talking about?
Yeah.
So what are we doing?
5.
So 5 plus t squared over the square root of t? You have to separate it.
Yeah.
So you have to write
That's why
5 times t to negative 1/2 plus the square root of t plus t to 2 minus 1/2. So let's do that. So y equals, one more time, is 5 plus t squared over the square root of t. Is that correct? Is it 5 plus t squared over the square root of t?
Yeah.
Okay, so we will separate it as 5t to negative 1/2 plus t to 1/2 plus t to 2 minus 1/2, which is 3/2. So what I did was I separated the fraction into 3 fractions. And 5 over this becomes this. t over the square root of t becomes this, and t squared over the square root of t becomes that. Is that okay? And now we can differentiate. So y prime equals, bring down negative 1/2. So negative 5/2 t to negative 1/2 minus 1, negative 3/2, plus 1/2 t to 1/2 minus 1, which is negative 1/2, plus 3/2 t to 3/2 minus 1 is 1/2. I don't know how they want the answer, but what I would have,
The antiderivative.
I'm sorry?
The antiderivative.
Oh, we're not differentiating?
No.
Oh. We are integrating this?
Uh-huh.
Oh, I'm sorry. Sorry.
Fine.
I forgot. I didn't pay attention. So we want to find the integral from 5t to negative 1/2 plus t to 1/2 plus t to 3/2 dt. And we want the most general antiderivative. So then it says 5 t to negative 1/2 plus 1, which is t to 1/2 over 1/2 plus t to 1/2 plus 1, which is 3/2 over 3/2 plus t to 3/2 plus 1, which is 5/2. I prefer adding than subtracting, to tell the truth, so it's much better. So now we flip all this. 10, the square root of t, plus 2/3 t, the square root of t, plus 2/5 t squared, the square root of t. Again, I don't know how they want the answer. You can pull out the square root of t if you wanted to. I wouldn't do anything else. Sorry, I thought we were differentiating.
Plus C.
Of course, it's the most general, yes. Minus 1 point for me. Yes, I just said that and I rushed to talk instead of finishing it up. Sorry, my fault. Can get away with anything in this class.
So is it you flip the denominator, like for the 2/3t square root of t, you flip the denominator?
For this one,
Yeah, so it cancels out.
Yeah.
so I get 2. So it's t to 3/2, which is t to the first power times t to 1/2. Is that what you meant?
Yeah, well, yeah, I see you got the 2/3, you flip the
Yes.
denominator.
Yes.
And then, okay, t times, okay, gotcha. I see, I guess t to the first, and then, t squared
Yeah,
is t to 1/2.
so when you take the square root from t to the third, you have t squared and t, and you take the square root from t squared.
Yeah,
However, to be exact, the square root of t squared is the absolute value of t, but we assume that all conditions are fulfilled.
gotcha.
Yes, I'm ready.
Oh, I just said like from the first test number to infinity to infinity, that's 2 plus
Yes.
5.
Yes. So let's take a look at this. So we have limit as x approaches infinity, 2 minus e to the x over 5. Was it 5 plus?
2 plus 5 is good.
Very good. So now we know that, and we know from the very beginning of limits that I have to plug it in. So this is a nice situation because it's infinity over infinity. So I will use L'Hopital's rule, which we did not know at that time. Negative e to the x over 5 e to the x. We simplify and we get negative 1/5. It becomes more convenient now because we know L'Hopital's rule. Any questions?
This one right here.
Yes. Yes. For this one, I recommend rationalizing. So this is limit as x approaches infinity from the square root of x squared plus x plus 1 minus x. Because the problem is it's infinity minus infinity, which is one of the 7 indeterminate cases. So we can't use L'Hopital's rule or anything else here, so I recommend doing this. The square root of x squared plus x plus 1 plus x, and the square root of x squared plus x plus 1 plus x. So then limit as x approaches infinity. The numerator is x squared plus x plus 1 minus x squared. And the denominator is the square root, and I will factor out x squared as we remember, 1 over x plus 1 over x squared, and plus x. These two go away. Because x approaches infinity, this piece in a moment will become limit x approaches infinity. I factor out the degree at the top. And I factor out here the square root of x squared times the square root. This is a product. I'm allowed to write the square root of this times the square root of this because it's a product. With a sum, I cannot do that. So the square root of x squared will be x only because x approaches infinity. And then the square root of 1 plus 1 over x plus 1 over x squared and plus x. And you see the common factor goes out. And that's exactly what we wanted to get rid of. And now the numerator goes to 1, and the denominator goes to 2. Because all the 1 over x squared, they go to 0. Any questions?
So how did we get the x squared? Did you take out the x, and that's how you got 1 plus 1 over x plus 1 over
Yes, I have to.
Okay.
Yes.
And then for the bottom, the last line that you did for the denominator. was
So
that x
you're
times-
talking about this part?
No, all the way on the bottom.
So first of all, here I factor out x, and x times 1 is x, and x times 1 over x is 1.
Right.
Here I factor out x squared because that's the degree. X squared times 1 is x squared times 1 over x is x squared times 1 over x squared is 1.
Okay.
And the square root of x squared should be the absolute value, but since I know it goes to infinity, positive, that this has to be x.
Okay.
And then this is a product, and from this product, I factored out, from this sum of two terms, I factor out x, and then I still have the square root, but plus 1 from here. This times this is this piece, and x times 1 is this piece.
Okay.
And that allowed me to simplify the x from the top and the x from the bottom. And now I can apply the limit when x approaches infinity. This is 0, this is 0, this is 0. The numerator is 1, and the denominator is 2. This one and this one.
Gotcha.
Better?
Yep, thank you.
Thank you. Good. Anything else? Yes, please, Eddie, go ahead.
Would you mind doing a precise definition?
No, of course not. Give me the function, any function you want.
It's limit
Limit as x approaches.
3.
Very good.
3 plus 1/3 x equals 4.
Like this. Good, indeed. Yes, 3 plus 1 over 1/3 x when x approaches 3. Yes, that's correct. So all we have to write is that this is equivalent to, for every epsilon positive, there exists a delta positive such that every time we pick a number close to x equals 3, less than delta, this will always guarantee that the function will be close to 4. The function value will be close to 4. How close? The distance is less than epsilon. So I always start here at the end with 1/3 x and -1. I know what I'm after. This is what I'm after. This is what I want to see at the end. I will find the least common denominator, x minus 3 divided by 3. I am allowed to separate the absolute value of a ratio like this, but I have to write this particular step. Now I will change this into 3. And now all I have to do is multiply both sides by 3. And now this final step is by comparison. I have x minus 3 in absolute value? Yes, I do. And this must be delta. So therefore delta equals 3 epsilon.
Can we use a different symbol for epsilon for y?
If we would use what?
Can we use a different symbol for the epsilon or
Mhm.
signal?
No. Epsilon
What is
delta.
epsilon?
Epsilon delta.
Is there, so, well, I understand we use the absolute value. What would we do if it was a negative in the denominator? Would we set it in a positive?
Right.
Distance?
Yes. Yes, because so let's suppose I have here -3. It would be the absolute value of -3. This still changes into 3.
Okay, because we are just looking for that distance from,
No, it's the absolute value of -3. The absolute value of -3 is 3. Yes. And yes, the distance will be positive no matter what. Yes.
I think we did this problem in class before, but can we do it again?
Yes.
The
Which one?
number 1.
Number 1, yes. Good. So here's number 1. So limit as x approaches 0 from the right from the square root of x cosine pi over x. And of course, when we plug in 0, we get 0 times d and e. And you can say, well, that's 0. Well, possible, but I have to show. Cosine of infinity is, I have no idea. So, first of all, we're going to write the fact that cosine is a bounded function. Cosine goes from -1 to 1. It cannot be lower than -1, it cannot be more than 1. Now, of course, I need to build this function, and I do have cosine, but I have to multiply all 3 sides by the square root of x. I can because it's positive and not 0. So now I have negative the square root of x less than or equal to the square root of x cosine pi over x less than or equal to the square root of x. And at this point, this is the first hypothesis of the squeeze theorem that says that I found 2 functions, f of x and g of x, that squeeze the given function between themselves on the interval such and such. So 7, 8. So that's the first step. In step 2, I have to find the limit of negative the square root of x when x approaches 0 from the right, and limit of the square root of x when x approaches 0 from the right. If these 2 exist and are equal, then all conditions, all hypotheses of the squeeze theorem are fulfilled, and I can make the conclusion. So the answer is, for both, is 0. They both exist and they are equal. Therefore, from 1 and 2, by the squeeze theorem, we conclude that limit from the square of x, cosine pi over x as x approaches 0 from the right must be 0.
Can we only use that, can we only use the sandwich method for trigonometry?
No. No, we had examples in which we were not even given the function. But we were given the first condition. We were given that the function was squeezed between two. So we did not have to develop or show the first step. It was already given to us. Or a function that was completely unknown. So that is a possibility. No, not only for trig functions, but I can't think of anything that is that would work unless we are given the interval on a function that is not bounded. Unless we are given the interval. So there are other possibilities, not for trig functions only. Very good question, thank you.